Who's not tracking with me on this? Does anybody have a question that I can answer specifically?
Or not a question,
Or not a
just
question,
what the heck
like,
are you talking about?
Does everybody understand what we're saying when how pressure and temperature are related? How
Heat
we,
and temperature aren't the same thing.
yeah, or how we move the heat energy? We're all tracking?
Good, I love this,
What-
perfect.
Will the outside air always be hotter or cooler than the refrigerant?
It has to be in order for us to get rid of the heat.
Yeah, you have to, yeah, if it were hotter outside than the refrigerant, then it wouldn't work. It has to, but it won't ever be that way, because, right, because of just the way, if it's hot enough outside that it's like 100 degrees outside, then inside the home, we're absorbing enough heat energy, our compressor will ramp it up hotter than whatever the outdoor ambient is.
If ever the discharge is not hotter than outside, your compressor is broken,
Yeah,
not running, or you have no refrigerant.
yeah. So it will always be that way.
Yeah. And it always must be.
Yeah, otherwise there's no incentive for it to move and it won't work.
Let's say that on our evaporator coil, so we've dropped pressure. And why did we drop pressure?
Cool it.
To cool it, 100%. We need to change the temperature. The only time we're changing pressure in an AC system is because we want to change temperature. And pressure is our convenient way of doing that. We could run the refrigerant through ice, get it nice and cold before it comes in. Well, and then on its way out, we run it through fire, get it hot, right? We can change the temperature different ways. But that's a very inefficient way of doing the same job. When you have something that can manipulate pressure, you have something that can manipulate temperature. But it doesn't just change the pressure through the metering device. What else happens to that refrigerant?
The state changes,
The state begins to change.
or
Yeah.
starts to boil.
Yeah, so we have our system that is very high pressure and the liquid molecules are being pushed together. They were cooled off, so they relaxed enough to form, but also the pressure is holding them into that liquid state. Pressure helps those molecules bond, and when they bond, that's what we call liquid. And so we have both the pressure and the cooling down of the refrigerant, so the molecules aren't going crazy, then the pressure, and it's holding it together. As soon as it drops in pressure, now those molecules can begin to move and separate. It starts boiling. Also, we learned that when we drop pressure and the molecules aren't forced together, they relax, they calm down. We call that temperature change. It gets cold. So that's why it starts boiling, is because it immediately drops in pressure. And that's why it's also cold, because it immediately drops in pressure.
Who can give me the three phases of matter? The three main phases of matter. Does everybody know what those are?
Solid refrigerant gas.
Cool, awesome. Where am I gonna find solid refrigerant in my system?
Maybe on food or something.
If it freezes.
No.
Solid refrigerant?
Oh, no, you're not.
No.
Never, right? If I have
So
solid,
we have freezing in an AC. What's freezing?
Water.
Yeah, and where's that water coming from?
Condensation.
And where's the condensation coming from?
The air.
Air.
Yeah.
Yeah.
air, exactly, yeah.
What we're breathing right now, there's plenty of moisture in there to make a coil coated completely with ice. Giant chunk of ice, gonna take 6 hours to melt.
For sure.
This is a heat pump.
And that's all that moisture in our air. Condensating, freezing, but the refrigerant never freezes.
No, it should not. If your refrigerant is solid, then you have bigger problems. Like the end of the world. So in our system, we only ever see liquid and vapor. Liquid refrigerant we're gonna see in our condenser and going into our metering device. As soon as we pass through here, we still see some liquid. We're boiling, we're evaporating in here in the evaporator and turning it into vapor. So these the job of these two components is in the name, right? Like pretty much everything, it is, those are intuitive the way they're named. It's not a trick, right? The compressor compresses, it condenses in the condenser, it evaporates in the evaporator. Those you can trust. This one I'm not so sure about, but
It meters the flow.
yeah, but it's called a metering device. We also call it a TEV or a TXV.
Yeah.
Sketchy.
It's a little bit harder on
Yeah.
that one, but it drops pressure.
But we see, so phase change is very important to what we do. We have components where we're changing phase of our refrigerant, right? And there's a trick here that lets us move heat energy really efficiently, right? So we have liquid and we have gas. I can manipulate so water boils at 212 degrees Fahrenheit, right? And water freezes at 32 degrees Fahrenheit. But what you see on the slide there is a phase diagram, so I can change the temperature at which water boils or the temperature at which it freezes by manipulating the pressure and the temperature. So Bert had a story. Not too long ago he went camping, right? And he had, you wanna tell the one about Colorado and the
Oh yeah, sure. Sounds great. I went actually North Carolina and we were up about 5,000 feet elevation on a mountain. And they had the same electronic boiler that I have at home when I make tea. And at home, I set my electronic boiler to 212 degrees. So that when the water hits 212, the alarm goes off and I'm ready for tea. And 212 is where water boils, right? Okay, so then I went up in the mountains and they had it set to 208. And I was like, okay, somebody doesn't like their hot tea, put it on 212, started it, the alarm went off, I came in, there was no water.
Does anybody know why there was no water left for Bert's tea?
Difference in pressure.
Pressure, because you're in a higher elevation.
Okay, what did the change in pressure do to the boiling point?
So like decrease it.
Yeah.
Okay, it decreases it.
Yeah.
Yeah, I was just gonna say, like, when you have the lower pressure, like, all the phase change is lower.
Right.
There's a lower pressure, and then it just, it boils off, and then it's the same with the refrigerant, because it's weird, that's what's confusing to me before, because I was like, why is it boiling at like 35 degrees, and then it's condensing at a higher temperature, like, that's whack. Because water boils at a higher temperature than, but then I realized, oh, that's why we have the metering device, that's why we have the compressor, because it's allowing it to do that.
When we change pressure, so I can change pressure or I can change temperature and I can manipulate the point where that phase change happens. Did anybody see at the HVAC symposium when the guy was boiling water at the room temperature?
Yeah.
Yeah, you saw that one? I don't know if the videos are up yet, but basically, if you ever seen this in science class, they'll do this thing where they'll take a beaker of water and put it under a bell jar and pull a vacuum on it, and all of a sudden it starts boiling, right? Because you've changed the pressure. Things will boil at room temperature if you decrease the pressure, right? You can do that with water, it works with any substance, right? It works with our refrigerant. So when we change the pressure, we change the point at which it boils. Or condenses, right? We can also ramp up the pressure and make that condensing point a lot higher, right? That phase change is going to be critical to how much heat we can move. Because when we're boiling or when we're condensing, we're actually moving a lot more heat energy than when we are just gaining temperature, right? There's something magic that happens at boiling, right? Beyond just bubbles.
So back to the tea story, if boiling point happens at 208, where I was at elevation, then what happens is I'm putting tons of energy heat into that water. It's heating up, right? As soon as it hits 208, it starts changing state. All the heat that I add to that water does not make it go above 208. It stays at 208 because whenever something is changing state, it doesn't change temperature until it finishes changing state. So now all the heat that I added to that water was being used to boil it, but it wasn't being used to change its state. At first, the water was 70 degrees dump 70 degrees in there, start adding heat. I'm adding tons of heat, it's slowly coming up in temperature to 208, it begins to boil. Every bit of heat I add changes the temperature while it's a liquid. But as soon as it goes into saturation, where it's now changing state, still a bunch of liquid, but it's also boiling, all the heat that I add doesn't change its temperature, it stayed at 208. And all the heat I added was being used, it was being absorbed and being used to boil it. So by the time that it finished boiling, all the rest of that liquid, then there was nothing in that teapot except for vapor. And it went up to 212 really quick. You added heat, it went up to 212. It became superheated, and you can't make tea with superheated liquid. It's just air. So that's what happened to my tea. So then I had to restart and put the timer at 208. So once it hit its boiling point, it let me know. And I had water in there, which also means that I now have to make my tea at 208 temperature. In order to make my tea at 212, if that was crucial, I would have to boil inside of a pressurized tank. So you guys have heard of pressure cookers, right? That's so that we can make our boiling point way higher. It holds pressure, and as you increase the pressure, you increase the boiling point. So water inside there could get to 300 degrees without boiling, and we do some really fast cooking under a pressure cooker. So same thing with refrigerant. The reason we use refrigerant instead of water in an AC system, any ideas?
It's easier to manipulate.
Lower boiling
Right.
point.
Yeah, lower boiling points.
Yeah.
Yeah. It's easier to manipulate because it's lower boiling points. Because refrigerant boils at 212 at 0 psi, do you know what temperature it takes to boil 410A at 0 psi? Let's find out. All right, you don't need the gauge anymore. If you look up at the screen, this gives us a digital, but I like the gauge because you can see the range. You can see the whole thing. As you change pressure, you're changing, and that one's more fun because you can actually change it. As you change pressure, you're changing the boiling point, right? Yeah. So here at 0 psi, 410A, minus 60. See that? So water boils at 212 degrees at 0 psi. Refrigerant 410A boils at minus 60 at 0 psi. Huge difference, much lower boiling point, which means we can manipulate it for some sweet cold temperatures that we can control. Water, we could do the same thing, but we'd need equipment that could handle really high levels of PSI and really low levels of vacuum. We would need some very extreme equipment, one creating a vacuum, one creating, well, we would have the high PSI whenever we tried to smash water.
Yeah.
So, or vapor. So, we're just gonna, reviewing is great, we're gonna step back because I just heard my system come on.
Okay.
And,
And we're gonna cover this again in a little bit, and
So
we're gonna
many
look at it from
times.
a different angle.
I was gonna tell you, don't be afraid to ever go ahead,
Okay.
because review is totally cool. If the
Alright.
explanation naturally leads you into each step that we're gonna hit again,
Gotcha. Yeah.
That's
'Cause
the
we're
way
gonna
fine.
go play with saturation and stuff like that. But I think we'll just finish this up for now. So we talked about pressure at the beginning. Let's talk about suction pressure and suction saturation real quick. So we've got our, we usually take our pressures at our condenser, right? When you're doing your diagnostic, you've got the big line, right, which is your suction line. You got the little line, which is your liquid line. Suction line is also sometimes called the vapor line.
the discharge on a system is inside the condenser. Unless you're on an RTU, you can actually open it up and grab it, which is convenient. But for us, it's locked inside the condenser. You can't go put your hand on it while it's running. So I brought the discharge inside so you guys can touch it. I brought straight from the compressor this line inside. How did I bring it inside?
Heat mode.
Heat mode.
Bingo.
We have an R22.
I don't know.
We have a heat pump system, and the reversing valve switched the direction flow from here to here. And so our suction line is now our discharge. I'd like everyone to jump up real quick and carefully touch it. It will burn you if you hold your hand on it. It's hot enough to make you dance if you hang out. And we're gonna do another round of guessing.
119.
That one's not bad. The other one was terrible. Nice and warm, huh? Anybody wanna guess?
119.
119,
That one's usually shoot the pilot valve.
130.
130,
136.
36. You know what your water temperature is at home when it's hot?
Should be around.
120.
120 is like a standard. Yeah. That's hotter
That's
than
the
your water.
hottest
That's
you can
hotter than
get.
your water.
Yeah.
No, it's just kind of a standard. People will sometimes go up in the 30s.
Before scolding, before you get burnt.
You can change it in here.
All right, it's the suction line. When you first started touching it, it was 150. It's rapidly climbing because it is both warm outside and warm inside. So 162 right now, the suction line. That's your discharge temperature. And yeah, like I said, it was 150 when you were first touching
Again,
it.
is in heat mode. You touch that.
Gravity looks right.
You can see our pressure.
Not bad.
Our pressure's maybe just a bit higher, right?
Yeah.
About 100 psi higher.
Is that on the suction side?
No, it's on the liquid side.
Okay, I was gonna say.
But it's liquid here,
Oh,
not passive metering device. It's a cheat. Yeah. So the point that I want you guys to take away is that line you felt that was 40 something degrees, 48 degrees, is the same heat that you're feeling right now in this line.
Just
Different temperature.
Different temperature, same heat. So the compressor took that and smashed it and put it out on the discharge line. You touch that and you think, oh wow, there's way more heat here than there is on the suction line. No, same heat. It's just way higher in temperature. That heat came from our suction, got smashed, and became 160. We didn't add heat to it, we just smashed it. We just increased its temperature. Same heat. Just wanted to get a little visual.
Yeah, Alex.
When you touch something and it feels cold to you, it's because that area of your body lost its heat. Like you said, that heat went into the suction line. So when you first touch it, you don't have an accurate reading of maybe how cold you think it actually is. As more of that heat in that area leaves your body and moves into it, your nerves are picking up like, holy, what happened?
Your temperature sensors calibrate.
But they're not actually feeling.
Your temperature sensors calibrate.
You're not actually feeling the cold line. Like we think like, oh, my body's feeling that it's cold. No, your body's feeling the heat leave your hand.
Say taking a hot shower and you're cold, right? Kind of similar to the same thing, right?
It happens.
Yeah.
Yeah, which is like, yeah,
Yeah.
that's exactly right. Mhm.
that's all the longer, the less hot it is.
Except for now heat's going into your body.
Exactly. So you felt cold before, and the water was hot once you got in it. But then once you're in it for a while,
Yep,
Your body's
everything's
kind of
adjusted, your body's
Yeah.
adjusted.
When you take a cold shower, you're just like rejecting heat from your body.
Nice. Alright, thanks for the interruption.
For real.
For real though, it's like body in shock, bro.
Let's hang out with suction long enough to feel comfortable with the rule of thumb and all of this. It's really good.
Okay.
Very useful.
So first, let's divide our system. We've got two sides that we usually refer to. We've got the okay. So there's a line right down the middle here. This is the low side, and this is the high side. Right?
Good job.
This is low pressure, and this is what?
Good job.
You're good at this. You are. We just had a little oops. And that went way better. Yeah.
High side, low side, right? So I want to know the pressure on my low side is going to be the same from here to here. right? All through the evaporator coil, all through those lines, it's always gonna be one pressure. Same thing is true on the other side. After it leaves my compressor, all the way from the compressor back to where it hits the metering device, that's gonna be the same pressure throughout all of it, right? So when we're taking pressures, we measure our low side pressure and we measure our high side pressure, right? And we can do both of those at these little ports here at the condenser, right? That's the most common access point in residential systems. So but when we're taking our pressure at our ports, my suction line, when I put a pressure probe here on my suction line, service port, I'm gonna get the pressure for my evaporator coil, for everything here, like all through this line. So let's name these lines real quick, actually. I can read it at the end. But does anybody know the names of all the lines?
All
that go-
four.
All four?
Yeah, I think so.
Okay, who wants to give it to me? Go for it.
Is it discharge
Okay, where's the discharge?
to the compressor to the condenser,
Okay, discharge.
and then
From the condenser to the meter device?
is it the suction line?
From the condenser to the metering device?
No.
Nope, not suction.
I'm trying to think.
Liquid line.
Liquid line, okay, I got liquid line.
That's suction line.
Alright. Suction line would be from evaporator to
Evaporator.
condenser, and then here's the tricky one that most people don't know. What's that one called? Yes.
Expansion line?
There we go.
Look at this guy, the new guy. Somebody went home and was watching some videos last
Wow, the
night.
expansion line. And so most of the time, you don't see the expansion line because in residential systems, your metering device is mounted on your evaporator coil. So your expansion line is about this big.
This right here.
Yeah.
This is an expansion line on a most coils.
Does anybody know on what kind of system I can see my expansion line?
A very long expansion line.
I mean, don't you see it on? You see it on carriers. I mean, you see the thing and it splits off.
Oh yeah, you can see it.
Yeah, you can see it in
He
the
means,
coil. I mean like.
Which ones have a long line?
Yeah.
Oh, long line.
Mostly package units.
No?
Nope, that'd be an
That's
so
the
short one.
opposite.
Yep.
Lennox train.
Mini splits. Mini splits. Who has worked on a mini split system before?
I have.
Yeah, Kieran, I know you've installed them. You've installed them. Alphonse, you've seen them? Cool. So mini split systems, there's still two lines coming to and from your condenser, but at a mini split, your metering device is actually in the condensing unit. That indoor unit is only a coil. So what that means is that if we're getting metered in the condensing unit, that second line that's going to the coil is the expansion line. So that whole long thing, right, is filled with saturated refrigerant.
What happens when we drop pressure? What happens to the temperature of this?
Change.
Just a lower temperature.
Lower temperature, right? And how low? How cold? Any ideas? It ranges
Probably close to 35 degrees.
35 to 45. That's usually our range, and how cold our saturation point is, or how cold our lines are. Yeah. And we've started boiling. It's still mostly liquid, but when things are that cold in our world, what do they do? When they, what's that?
I was gonna say we insulate the lines, but
Yeah, exactly right.
That's where he's
Go
going
with it,
with that, yeah.
Charlie.
So if you ever look at a ductless line set, both lines are insulated because both lines will condensate,
that makes sense.
right? On normal residential split systems, like you'll see here, we've got the suction line insulated, but we don't have the liquid line, right? Because it is a liquid line, it's not gonna condensate. But on a ductless, if this were a ductless system, both those lines would need to be insulated because one of them is actually the expansion line and the other one is still a suction line.
And they do that because ductless are made to be compact, right? Really tiny, as little as you can put inside, the better. So they put the metering device outside, more room for it out there than on the inside unit.
So let's get back to suction pressure.
Yep.
So we've got our high side, we've got our low side. If I put my probe on my suction port at my condenser, I'm gonna know what the pressure is all across the low side of my system. The only reason I'm looking at pressure is because I'm really curious about what the temperature is inside my evaporator coil. I'm looking for a magic number called my saturation temperature, right? Saturation temperature is the temperature at which the refrigerant is going to boil or condense. depends depending on which way I'm going. So in my evaporator coil, I'm looking at what temperature is it gonna be in that coil when my refrigerant boils. That is my suction saturation temperature. And when you're doing diagnostics, I got a rule of thumb that I like to use, which is I want my suction saturation to be 35 degrees, give or take about 5 degrees, below whatever the indoor ambient temperature is, which I can measure at my return funnel, or with the return probe if it's got like a direct return. So 35 degrees should be the difference there, okay?
And that's designed by, when manufacturers are designing equipment, they're gonna size the compressor, the metering device, the size of the coil, and CFM to try to hit that balance point, that 35-degree balance point. And you have plus or minus on there because you're changing. There's in the real world you have CFM changes, you have a little bit of refrigerant flow changes, but yeah.
And if I have, there is a little bit of play there, but if I see significantly low or significantly high, then that is an indication for my diagnostic that something's wrong. If I've got low suction saturation, I can have an airflow problem, I can have a charge problem. If I have suction saturation that's much too high, I might have a fan speed that is set too high, right? I'm not balancing my heat load with my refrigerant circuit.
What's
So-
another word? So he has 35 degrees below indoor ambient temperature. What's another word we use more commonly in the trade for that indoor ambient?
Room temperature?
Nope,
Dry
we do
bulb.
use room temperature a
Yeah,
lot.
yeah.
Indoor dry bulb.
Okay, those are all the same thing, but
Yeah.
there's one we use more commonly. When you call someone for tech support, they're gonna ask you, what is my, who said it?
The delta T.
Okay, it's part of the delta T, it's half of it. We have our supply and our
Return?
return air. Yeah, return is the other version of saying indoor ambient or indoor dry bulb or room temperature.
Which is,
But
sorry.
the return is the most accurate, so you could walk around in here and have 68 degrees. The return is pulling from the ceiling, could be 78, depending upon how high your ceilings are and how much heat there is in the space. So the return is the accurate place to measure from what my system is taking in as the indoor ambient. From my return air, 35 degrees above that should be my suction saturation.
I was gonna say, I've seen, a lot of times people just look at the thermostat, and the thermostat's reading, that's the indoor ambient air temperature, but that's not as accurate as actually putting the probe and seeing what's really going into the system, because the thermostat might be off, or it might not be taking into account the fact that there's a hole in the attic ductwork somewhere, you know? So, with those two things, we can figure out, are we within our rule of thumb? My return air temperature, and then looking at my suction pressure, which on Measure Quick, you can see on this dial, you see that the pink ring,
Mm-hmm.
right? That pink ring is giving me saturation temperatures, and those correlate to pressures on the outside dial. So the outside dial is giving me PSI, that pink ring there, is that 14? Yeah.
Yeah, pink is 14A, yes.
So that pink one is giving me, at this pressure, what is the saturation temperature? And you can see that on Measure Quick, right? When you look, the Measure Quick has the dials set up just like the analogs, because that's what everybody knows. So that center number that's in the center of your dial is your saturation temperature, right? The number below it is a PSI, is a pressure. They're always correlated, right? You can see that that's the reason we have PT charts, right? Is there's always a temperature, correlation between pressure and temperature, and it's mapped out. That's why so when we play with Measure Quick, right, as soon as I put on my probe, right, it'll give me not only the pressure, but also a saturation temperature that then correlates to that pressure. It's got programmed in it, that PT chart. This is a visual PT chart, right? I see that there is wherever pressure I'm at, there is going to be a temperature associated with it that is the saturation temperature, or my refrigerant will change state.
So let's say you called me and I said, what's your evaporator temperature? And you were like, I don't have access inside the house. And I'm like, okay, are your gauges hooked up? Yeah. Okay, so your suction should tell me what your evaporator temperature is. Well, how can we know from outside of our condenser on our suction what our evaporator temperature is.
Your saturation.
Whole low side and the saturation, exactly. One, it's all the same side, it's low. So we're measuring the same PSI inside the evaporator as we are out at the condenser, right? But if we have, if we know what that PSI is, somebody give me a suction number.
139.
139, ooh, nice and warm. I'm gonna get up, okay, I'm just gonna get 125, because that's easy for me to find. Thanks for saying 125.
139.
At 125, what's our saturation?
42.
42. Boom. So, if saturation is happening somewhere in our unit, and our PSI is 125, then we know wherever saturation is happening, it is exactly 42 degrees. Because that's what our pressure is. They are always tied together. This is a very consistent, constant science. So, if our metering device is creating saturation, it's creating the boiling point, and that saturation is happening as it travels through the coil until eventually it finishes and becomes fully vapor, then we always know, based on the temperature or the pressure, what temperature our coil is. Now, if our coil was not in saturation, let's say the system's off, it's not running, and we still had 125 PSI. We would know at 125 PSI, 40 degrees is where saturation happens. But because the refrigerant's not moving, it's not flowing, it's not actually in saturation, we're not boiling, we're not actively boiling. But if we take that refrigerant sitting there at 125, 40 degrees, it's still in saturation. You add a little bit of heat to that, it's boiling. You remove a little bit of heat, it's condensing. It's still in that mixed state at 40 degrees. If we measured it above 40 degrees, we would know whatever's in that line is not saturated, it's vapor. If we took our clamp and we measured it, it was still at 125 PSI, and we measured it and it was 30 degrees, we would know that line was full of liquid. If we measured it and it's 40 degrees, we would know it's in saturation. It's in the mixed state, it has both vapor and liquid.
Is that constant, the 40 degrees?
It's gonna vary.
At 125 PSI, constant.
Okay.
Yeah, so wherever it's 40,
The pressure.
wherever it's at saturation, it's gonna be 40 degrees.
At 125 PSI. As soon as, and you can see on here, as soon as you change the PSI, you change where that point boils
Yeah,
at.
and that goes back to what we were talking about with the phase change, right? We can manipulate where that boiling point is based on pressure, right? By either dropping it or increasing it. And
So then I'm gonna ask one more question to see if it sinks in. If I take my clamp on a system that's running, so we know saturation begins after the metering device and goes through this system, it's in saturation. If I take my clamp on a running system here and it says 46 degrees, I'm gonna go on the expansion line, on one of these little lines right here, after the metering device, boom, 46 degrees. System's running, it's in saturation. My suction clamp says it's 46 degree line. Expansion line is 46. What's my PSI?
0, 138.
130 something.
Alright, let's go find it. Boom, there's my PSI. Right?
Yeah.
Yeah, I gotta do that.
You know your PSI because you know saturation happens. It's happening right here in the circuit. This is where saturation happens. I measured the temperature. So then I know that always, if it's in saturation, that always has an exact PSI that's connected to it. Or, we usually do it the other way around. The only reason we hook up one of these bad boys, where did that go? Oh yeah, it's on the screen. The only reason we hook up one of those bad boys is not because we want to know what the PSI is. We don't care about the PSI. We just want to know where the saturation is. What's the coil temperature? Where's the saturation point? Or, if you had just as easy access, you could always put your line clamp on the equalizer tube and get your PSI. but usually it's a little easier access to hook up the port right there. And that's on a running system that's doing its job. If you have a running system that's flat, then none of these rules apply, right? We're not actually we don't have liquid where we should have it, we don't have saturation happening where it happens. But on a system that's running, you grab the line, it's cold, it's beer can cold, liquid line's a little warmer, compressor's moving refrigerant. All you would need to do is hook up your, to the equalizer tube where there's saturation happening, and you could figure out your PSI. That's, so you'll notice a lot when you call people for tech support, they're gonna stop asking you things, what's my suction pressure, you're gonna hear things like, what's my saturation? What's my evaporator temperature?
That's really a number we're after. They don't make, like, PSI doesn't mean anything to them. That means they want the extra step where let's go and give you the saturation temperature, which you can look up on your PT chart or measure Google.
Who wants that?
Do it.
Who were you saying wants that?
Anybody that you're calling for tech support, they're gonna be
Oh,
curious.
tech support.
Yeah,
got it.
yeah. Or, so that means, if you're on the phone with somebody from a company or with one of us and we're trying to help you out, like, I'm curious about the suction saturation. If you tell me it's 150 PSI, that doesn't even mean anything to me. I'd have to look it up. So you give me the suction saturation temperature, that means something. I'm trying to balance temperatures, not pressures.
Can we, have them calculate where the suction PSI should be? Alright, what's our return?
69.
Alright. 69. It's Marty. It feels a lot warmer than 69 in here. What's our thermostat say it is?
71.
So we can't trust this room's ambient. Why is our return 69? You guys can figure this out.
Wait, what are you saying?
Our return is 69, that's air going into the unit. But if we look at a thermostat, it's 74 in here. And it doesn't feel like 69 in this room.
So the return is,
Okay, so the return right up there,
yeah.
you think it's 69 up there, but it's 74 here? You think the top of our room has hotter air?
Hot air.
Yeah, hot, right,
Cold air.
yeah, so
It would be hotter up there than 74.
yeah,
So that's not why. Any guesses? Look at the size of that return. You got like a 10 max, maybe an 8. Is that enough for that whole unit? No.
You need to make more.
So we do have more. This unit is cooling many other spaces that are right now enjoying the heat I turn on or when I turn the cool down.
Super cool.
So there are returns in all these other office spaces pulling air. And those office spaces are 69 or colder. So we have ours in the mix, but a lot of other returns. The rest of the office is experiencing some cool temperatures thanks to us being in the room where the thermostat is. We're heating up this room, it's trying to keep up. They're all freezing out. It's 69 in the return because it's pulling from many other rooms and all joining together in that column. So you can't just go, if we were to do our 35 degrees based off 74, rule of thumb you just taught us, our suction saturation should be 35 below our indoor ambient. If we just went off the thermostat, we would have very inaccurate, but we plug into the return, now we know what our system is experiencing. Alright, so now, rule of thumb, what should my suction saturation be if the return is 69?
44. Well, no, 69.
41.
41, okay.
Or
Wait, is it? Yeah, it's like it's a range. It's not.
It's,
always
no,
like-
we're just gonna go with the exact first, we can do plus or minus 5, but let's go with the exact listed right here,
34.
34. Why does that feel so perfect? You guys are so good at math, it's amazing. Alright, so, if it is 34, then you two can have a look at this, go ahead. If it's 34 saturation, then what should my PSI be when I hook up to my unit?
like 103.
Wait, 30. Like 110.
105.
No,
They go by increments of 5, right?
I have no idea.
Each little line.
You're on your own. Just give me some.
Yeah, it's like just over 100.
105, 106, yeah. So, if you were to hook up to 105, 106, you might be like, that seems kind of low. Because we're just thinking PSI. We're used to seeing a little higher than that. That seems kind of low. It's not low for the 69 degrees coming into this unit. That's right on target. So knowing what it should be before you hook up is actually makes your test valid. If you don't know what it should be when it hooks up, you shouldn't even be hooking up. So this is a really important one to hang on to, plus or minus 5 degrees. But what is the hot air coming into the unit? And plus or minus 5 degrees from 35, I should have my suction saturation.
We're gonna look at the same thing on the high side just briefly, where it's the same idea, right? We're hooking up to our liquid port this time for the same reasons.
Or discharge.
Or discharge. Well, yeah, or discharge, yeah. If you had a port on your discharge line, then yeah, you could hook it there too.
It's just a lot of these guys in commercials don't even have a liquid port.
Right, that's true.
But it's still the head pressure.
Yeah, so that's whether I take it at my discharge line here or if I take it at my liquid line here, it's gonna be the same pressure throughout again, right? And we're doing it for the same reason. I wanna know what my saturation temperature is this time in my condenser. So again, I want the pressure, which correlates to my saturation temperature. Same thing as on the low side, only now I want to know what's my condensing temperature. So it's going the opposite way. Instead of boiling, I'm condensing now, but the idea is still the same. Where's my saturation? So that way I can do some calculations. And again, I have a rule of thumb based on outdoor air temperature, somewhere between what I write 13 to 20 plus or minus 3, something like that. That one's a little bit more.
There's a little more range depending on condenser size and fin size or condenser fan size, speed of condenser fan. We're not trying to get as exact.
Yeah.
Inside we want it exact because we want to dehumidify, we want perfect comfort. Outside we just need to get rid of heat.
Yeah.
It has to be hotter basically.
My coil is, my indoor coil is what I'm mostly worried about. I'm calibrating my system based on that. This is sort of a consequence, right? This, I just need to make sure that it's hotter than outdoor by a good margin so I can reject heat efficiently. Other than that, I'm not worried about my coil freezing or something like that.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.